Okay, we're going to look at something called inverse functions. So let's just revise what inverse actually means. So inverse means opposite. So in mathematics, the inverse of +2 will be -2. The inverse of -5 will be +5. So inverse meaning opposite. So the inverse of multiplied by 3 is divided by 3. And the inverse of divided 7 is multiplied by 7. So we've done inverse operations before, so that should be familiar. So let's apply this to functions. The inverse of a function is an operation that undoes the original function. So the inverse relation of y equals 2x is y equals x divided by 2. Okay, because if you think of y equals 2x, it's y equals 2 multiplied by x. So what's the opposite of multiplying x by 2? It's dividing x by 2. Okay, over here, the inverse relation of y equals x over 3 is y equals 3x. So if you think about it, what's the opposite of dividing x by 3? It's multiplying x by 3. Okay, so this here is the inverse relation of y equals x over 3. And this here, y equals x over 2, is the inverse relation of y equals 2x. Let's come down to the other ones. The inverse relation of y equals x plus 5 will be y equals x minus 5. So the opposite of adding 5 is subtracting 5. Over here, y equals square root of x. What's the opposite of that? The opposite of square rooting is squaring, isn't it? So the inverse relation of y equals root x is y equals x squared. There is one obviously consideration here. X has to be bigger than or equal to 0, doesn't it? So technically, y equals root x only exists for x bigger than or equal to 0. All right, so there has to be a consideration in that question. Essentially, the opposite of square rooting is squaring. Okay, so let's have a look at the next one. The inverse relation of y equals x cubed is y equals the cube root of x. The opposite of cubing something is cube rooting something. Okay, just like the opposite of squaring something is square rooting something. Okay, so we've got the function, and then we have its inverse relation. All right, so let's have a look at a table of values now. So here we have a table of values for y equals 2x. Okay, so you can see here all of these y values have been formed by doubling the x values. Okay, so double 4 is 8, double 8 is 16. Right, because this is the table of values for y equals 2x. Now let's look at the table of values of the inverse relation y equals x over 2 and then see what's happened. So when x is minus 2, we put that into the equation, we get negative 2 over 2 is negative 1. And we put x equals 2 into here, we get 2 divided by 2 is 1. And we put x equals 4 in there, we get 2. And so on. So we're just halving the x values here. So it's going to be 4, and that's 8. Now have a look at the x values and the y values in the first equation, y equals 2x, and have a look. You should, in the second table, you should notice they've been swapped over. Okay, so these values here have been swapped over compared to this table here. All right, so you'll notice that the x values are now the y values of the inverse relation. And if you look at the y values of the original function, they are now the x values of the inverse. So our conclusion then is if we interchange the x and y values for the original relation, we obtain the inverse relation. Okay. So if I said to you, here's a table of values for my function or my relation, and I want you to find the table of values for the inverse relation, well, all you'd do is you would say, okay, I know that the x values and the y values are swapped over. So without even looking at the equation of the inverse, you can say, well, look, I know the x values and y values will be swapped over, so I'm just going to put negative 1, 1, 2, 4, and 8 there. And over here, now the y values now become the x values for the inverse relation. So negative 2, 2, 4, 8, 16. Okay, so if you take a function and you swap its x and y values, you obtain the inverse. Okay, let's just check that. If you start off with y equals 2x, and if I swap the x and y over, okay, I get, and I'll make y the subject, y equals x on 2. Okay, so by swapping the x and the y, I actually obtain the inverse relation. Okay, so step number 1 to find the equation of the inverse is you interchange the x and y values and then you rearrange the equation to make y the subject. Okay, so just going back to our original question there, here's y equals 2x. If I want to find the inverse relation of y equals 2x, I swap the x and y over, so I get x equals 2y. Then I make y the subject, so I get y by itself. And then this is the equation of the inverse, as you can see. There it is. All right, so let's do a couple of questions. Pause the video anytime you like if you want to just do the question by yourself. So to find the inverse relation for these, I'm going to swap the x and the y values, and then I'll make y the subject. Okay, so here I'm just going to subtract 1 from both sides. Yep, and then divide both sides by 2. That cancels. And then my final answer is y is equal to x minus 1 on 2. So this relation here is the inverse of y equals 2x plus 1. Okay, so let's have a look at the next one. So to find the inverse relation of this, you can pause the video if you want and have a go at this by yourself. Swap x and y, so x equals 7 minus 5y. And then we've got to make y the subject. Okay, so we're going to take 7 from both sides. So we're x minus 7 is equal to minus 5y. And then we're going to divide both sides by negative 5. Okay, negative 5. That cancels. And so your final answer, which we'll put up here, is y equals x minus 7 on negative 5. So this equation here is the inverse relation of this equation, okay? So this is the inverse of this, just by swapping the x and y, making y the subject. Now, just one final thing, that minus sign we can put up to the top if you want. And if we do that, you don't have to, but we could. So we could go y equals minus x minus 7 on 5, right? And then I could expand the brackets and that'll give me 7 minus x over 5. Okay, that's another way of writing that answer. Now you can pause the video anytime and have a go at these questions yourself, as I said before. Let's have a look at the next one. To find the inverse relation of this, I just swap x and y over, okay, and make y the subject. Now, the easiest way to make y the subject for these questions is to swap those two terms, and I get y is equal to 3 on x. Okay, so x equals 3 on y, and then y equals 3x. So we obtain the same equation as we started with. So that's interesting, isn't it? Swap x and y. So this is a hyperbola. So for this particular question, you can try this one as well. If we swap x and y, we get x is equal to 5 on y. And then I can swap these terms over, so I get y is equal to 5 on x. So it turns out that the relation and its inverse are the same function. Okay, now when you get down to this one, f of x equals 3x plus 1 on 4, you've got to think of this as y equals 3x plus 1 on 4. So now when I swap x and y over, I'm going to get x is equal to 3y plus 1 on 4. And then we've got to make y the subject. So I'm going to multiply both sides by 4 there. 4s will cancel. That leaves you with 4x. So you've got a 3y plus 1. Now I probably don't have much room here to work this out. So we'll try and do this economically for space. The next step is 4x minus 1 equals 3y. And then last of all, put that down here, you're going to get y is equal to 4x minus 1 on 3. Okay, so this is the inverse relation of this function here. Okay, now what about the last one there? The last one, we'll do the same thing. So we swap x and y. And then we have to get y by itself, i.e. making y the subject. So you're going to get x plus 2 is equal to y cubed. And then last of all, you're going to have to cube root both sides. Cube root there, cube root there. And then you have y is equal to the cube root of x plus 2. So that's your inverse just there. All right, now what about the domain and range? Let's have a look at this hyperbola here. The domain will be all x not equal to 2, and the range will be all y not equal to 0. Now let's find the domain and range of the inverse. So what we're going to do now is we're going to take the original equation and swap x and y over. So we get this. And then we're going to swap y minus 2 with x. Okay. Then add 2 to both sides and you get 2 plus 1 over x. Now, if you look at the domain for this, x is not allowed to be 0 because that'll give us a 0 denominator. So it's all x not equal to 0. And the range will be all y not equal to 2. Okay, because we get a horizontal asymptote at 2 in this case, so y cannot be 2. So what you should notice is that the domain and range values have been swapped around. So all x not equal to 2, that becomes all y not equal to 2 for the inverse. And the range, all y not equal to 0, well, that becomes all x not equal to 0. Okay, so the domain and range values are swapped over for the inverse relation. So that's what we notice. Okay, so we'll write that down. What do we notice? The domain and and range values have been swapped. Okay, so that's that page there. And last of all, we'll do the inverse relation of the line y equals x. Okay, so let's have a look at that. Okay, so we're going to have, we've got the line, this is the line y equals x here. Y equals x. Now, complete a table of values for y equals 2x plus 1. Well, that's already done for us, so no problem there. And we're going to plot these on the number plane. Okay, so we've got 0, 1. So plot that. Then we've got 1, 3. So plot that. And 2, 5. And 3, 7. Then 4, 9. Oh, I can't fit that in. That's okay. So what I'll do is I'll get a line. And we'll just get that line there. And we're going to start. Should we do a different color? And do solid green. There we go. So we're just going to draw a line through these points here. There we go. And then there we go. That should go through those points there. Okay, so that's my line y equals 2x plus 1. So let's label that. Now I'm going to graph the inverse. And we know that the inverse will have the x and the y values swapped over. So I'm just going to take those y values and put them in the x row. Whoops, just slip there. So I'll get 1, 3, 5, 7, 9 in the top row there. 1, 3, 5, 7, 9. And then I'll take the x values and put those in the y row. So that's 0, 1, 2, 3, and 4. Now I'm going to plot those points now. So I've got 1, 0 here. And I've got 3, 1 here. Then 5, 2. And then we've got 7, 3. And the other one won't fit, but that's okay. Okay. So let's take that line there. And we'll draw a line through those points. There we go. I'll just extend it a bit further. Okay, so that's our line, our inverse relation. Now, if you go back to y equals 2x plus 1, the inverse relation is y equals x minus 1 on 2. Okay, so let's write that down over here. So y equals x minus 1 on 2. So we've done the first two parts there, and we kind of cheated by looking at the answer from the previous page. So there we go. So we've done 1, 2, and 3. It says compare the points on y equals 2x plus 1. So let's just colour them in a bit so you can see where those points are that I plotted before. Here they are. Okay. Now what you should notice is that the distance between the points follows a similar pattern. So I'm just going to draw a line between those points. Actually, we'll just get rid of that. And let's change colors. Delete. Let's go to black, I think. Okay. Now, I'm just going to draw a line from that point to the other one. And then I'll draw a line from this point to there. And then I'll draw a line from there to there. And then we'll draw a line from here to here. Okay. So hopefully you can see now that the original function and its inverse are reflections of each other in the line y equals x. So what that means is that the point on the original function is the same distance from the line y equals x as the point on the inverse relation to the line y equals x. Okay, so this point here is a reflection of this point in the line y equals x. And it just means that the points on this function are the same distance from the line y equals x as the points on this function. Okay, and we can show that by putting some dashes on this. So this distance here is the same as this distance here, and that distance is also the perpendicular distance, that's at right angles. And this distance here is the same as this distance here, and that's perpendicular as well, and so on. Okay, so it says on number 4, compare the points. What do you notice in regard to the perpendicular distance from line y equals x? Well, the perpendicular distance is the same. Okay, so what we're saying is this distance here is the same as that distance there, for example. So perpendicular distance is the same. Now, what do you notice about the x and y intercepts for number 5? Let's have a look. Here's an x-intercept of 0, 1, and now for the inverse, because we're swapping the x and y values, the intercept is 1, 0. So the x and y intercepts have been swapped. Okay, so let's write that down. The x and y intercepts have been swapped. Okay, so here are some key points. The points on the inverse relation are a reflection of the points on the original function in the line y equals x. So if I come back up here, what we're saying here is that this point here, I'll just color that in a bit, is a reflection of this point here. Okay, and this point here on the inverse is a reflection of this point here in the line y equals x. So y equals x is your mirror line, okay? And you've got pairs of points which are mirror reflections of each other in that line y equals x, okay? Second point, this means each point on the original function is the same perpendicular distance from the line y equals x as the corresponding points on the inverse relation. So if you look at this, what that means is the distance from here, okay, so let's have a look, the distance from there to the line y equals x is the same as the distance from here on the original function to the line y equals x. And that distance is perpendicular, which means at right angles. Okay, and last of all, the x and y intercepts of the original function are swapped on the inverse relation. So have a look. X-intercept of 0, 1 now becomes the y-intercept of 0, 1 now becomes an x-intercept of 0, 1. And that is it.